One of the most important things in determining the age of the universe has been Hubble's law. Same Edwin Hubble who determined that everything in the universe was actually moving away from us via this Doppler redshift. And sometimes I think science is very elegant, meaning that you can explain something very complicated with something very, very simple. And that Hubble's law is a classic example of that. This is the equation for Hubble's law, and we will actually use this equation in lab. It's not a terribly complicated equation. V stands for velocity, the speed at which galaxies are moving away from us, what we observe from our location here on Earth. And if we can do that in kilometers per second, that's going to give us V. HO is Hubble's constant. Hubble's constant has weird units, kilometers per second, that we get from the velocity, over megaparsecs. Mega, which is 10 to the 6th parsecs, which are distances to the galaxy. And what Hubble's law basically says, if we take the velocity at which a galaxy is moving away from us divided by how far away it is, we get a steady constant, which is known as Hubble's constant. And we're going to be using that, as I mentioned, in lab. Now, why is this a big deal? This is a big deal because the value of Hubble's constant is the number one most important thing in determining the age of our universe. And so work being done in astronomy today, much of it is fine-tuning what exactly that constant should be. So accurate measurements of the age of the universe, as I mentioned, is totally dependent on the value we get for Hubble's constant. 2013, Hubble's constant was at 67.8 kilometers per second. Your textbook uses 71 kilometers per second per megaparsec. And this value is all going to be really similar, but it is going to vary slightly depending as we get better data about distances to galaxies and speeds of galaxies. So we are fine-tuning this piece of information. When velocity in kilometers per second is graphed versus distances in megaparsecs, the slope of that line is where we get Hubble's constant. And remember, Hubble's law also said that if things are only 3.26 million light years away, then they're going away from us at about 71 kilometers per second. Twice as far away, well, then they're going to be twice as fast. 10 times far away, 10 times as fast. And so this is really important in trying to back up or redo that movie to the beginning of the Big Bang. As we talk about these numbers and talk about the data, please keep in mind that astronomers make it look easy. Tyson, Brian Cox, George Smoot, are a few of them, thousands of really excellent, very smart astronomers who use lots and lots of math. Because as we try and measure these distances to galaxies, there are a lot of variables we have to take into account. The Cepheid variables, very useful, but there is error built in. They have to estimate and measure the luminosity of nebulae and gases and galaxies. And that all adds into errors. So sometimes if you get to the point where you go, well, why can't they know better? They're doing a pretty darn good job as it is. The other thing is they have to subtract the motion of a variety of other things. We are moving around the edges of our galaxies. And we are rotating around our galaxies, and we are moving towards galactic centers like our Virgo supercluster, and we are moving towards Laniakea. So there's lots and lots of motion that we, the observer, are in that has to be subtracted off in order to get the data that's accurate for the Hubble constant. And so it takes lots and lots of math. Every once in a while, I get students who say, Mary, I love this stuff and I want to be an astronomer. What do I have to do? take lots of math, if you really want to do this for a living, because of the fact that that's what is really necessary in order to make the big discoveries that are being done today. Now, in determining Hubble's constant and the age of the universe, one of the things that has been incredibly important is type 1a supernovae. Type 1a supernovae occur when you have a white dwarf and you have a red giant, and when that red giant expands to the point where it's past that Roche limit, so that the white dwarf gets a huge massive influx of matter, and then that white dwarf goes supernovae. When that happens, these are kind of a standard candle. And by standard candle, we mean that they are pretty much always the same luminosity. Well, if you have anything out in space that's the same luminosity, by changing and determining if something is very, very bright or a little bit dimmer or very, very dim, scientists can use that to guesstimate distance to each one of these objects. Well, back in 2011, the Nobel Prize in Physics was awarded to three people: Adam Rees, Brian Schmidt, and Saul Perlmutter, and those gentlemen got that Nobel Prize for using type 1a supernovae to determine distances to very, very far away galaxies. And without that information, we could not have accurate measurements for the Hubble constant and the age of our universe. Now, one of that being said, one of our authors, Alex Filipinko, when I've heard Alex speak, they only give Nobel Prizes to three people. That's the maximum number of people that can be given or awarded a Nobel Prize. And Alex was sort of the fourth one in line. And I remember him saying, how often do you get a chance to be the guy who almost wins a Nobel Prize? But this is a picture of many of the important scientists who were part of that team at the Nobel ceremony in Sweden. So all of this data that's been gathered, all this very complicated math that's gone into play, it has given us the best value to date for the age of our universe. At this moment in time, we think it is somewhere about 13.75 billion years old, with an error factor plus and minus of 0.11 billion years. Now, that is thousands of years of astronomy and mathematics and optics and motion and physics and chemistry that have gone into that number right there. The fact that we humans can actually know that to that accuracy is astounding in my book. And we will talk more about this Big Bang thing as we unfoil, but that's a big deal. All right, that will end this one, and we're going to come back and talk some more about cosmology.